Okay, under such situation whereby you wanted to modify your design so that you have an optimized parameter, so what will you do? Okay, think about it. Most likely you are going to go back to your CAD model, okay, and then you are going to modify the parameters or the design points in your CAD model, and then afterwards you are going to rerun the simulation again. Okay, if the result doesn't fulfill the criteria that you wanted, probably you're going to go back to your CAD model, modify the design points, and then rerun the simulation again. And this go on and on and on and on. Okay, sometimes you may not know what are the best combination of parameters which gives the best result, because it takes a lot of trial and error for you to really get the result that you want. Probably you want a reduced mass but a maximum stress value, for example. Okay, probably you want to reduce mass and you also want to have the lowest stress value. So such criteria, the process to optimization is very, very time consuming if you do it conventionally. Okay, so in this module, in this session, we are going to explore the capabilities of ANSYS Workbench to help you automate the structural optimization process. Okay, so let's do this. Okay, the first thing you need to do is to download the geometry file. You go to ULearn, you locate for week 12 structural optimization, and then in there you'll find a geometric file folder. You click that particular folder and there is two zip file, which is a gripper and also the triangular plate geometry file. So you just download the folder and you can find the downloaded folder in your download link. Okay, so in there you cut the file and paste it in your desired document file. Okay, the next thing you need to do is you need to unzip this geometry file. So right click and choose extract here, and the extracted file is located in the same folder. So you'll find two zip file, which is a gripper zip file and also the triangular plate zip file. So before you unzip that, probably you can just delete the original geometry file so that you can save up the space in your computer. Okay, the next step is again unzip the gripper file, and also you need to unzip the triangular plate file. Now, since the two geometry folders have been extracted, you can again delete the zip file so that you can free up the space in your computer. So now, if you open up one of the geometry folder, let's say the gripper folder, there should be two items in it. The first one is the geometry workbench file, and the second one is the gripper file folder. Okay, so make sure these two items is located in the same folder. Okay, the same goes with the triangular plate. There will be one geometry workbench project file and also the project file folder. Okay, ready? So for our first case study, we are going to simulate for the mechanics of a flexible gripper. So this is how the flexible gripper looks like. What happened is that when the gripper is actuated at this particular point in this downward direction, correspondingly, the gripper will create a kind of gripping effect at this upper end point here. Okay, so for this particular simulation, we are going to assume the two end here to be a rigid point, as in it doesn't move. Okay, now we have two missions to accomplish. The first one is that we need to perform the computational simulation for the gripper mechanics, and our second mission is to optimize the parameters of the gripper geometry so that we can improve the gripping efficiency. Okay, let's do this, guys. From your workbench, you can open up the geometry file which you have downloaded from the ULearn earlier. Okay, you click the open folder icon here, find for the upper flexible gripper folder, and you open up the workbench project file. Okay, so now you can check on the design feature of the flexible gripper by double-clicking on the geometry tab here. So as usual, ANSYS will open up its design modular window. Okay, as you can see here, only half part of the gripper is being modeled. So if you look into the flexible gripper design, it is actually a symmetrical kind of structure. So only modeling one side of it is sufficient for the simulation process. Okay. Furthermore, when you only simulate for one side of it, you can apply symmetrical feature, and most importantly, you can actually expedite the computational process. Okay, now if you want to look into the details of the design points, okay, you can click on the XY plane. Okay, double click on the XY plane and you will see all the parameters connected to each point of the flexible gripper. So this flexible gripper is defined at 7 points, by which we label it as P1, P2, P3 until P7. Okay, so the design parameter is detailed out in the sketch toolbar over here. Okay, now we'll close up the design modeler, and now we are going to assign the materials to our flexible gripper. Okay, so you double click on the engineering data, okay, and then you make sure that there are POM materials being defined in the engineering data. POM stands for polyoxymethylene, or it is a kind of plastic polymer. So click on the POM and just have a double check, make sure that the Young's modulus is defined at 2 gigapascal or 2000 megapascal, and it have a Poisson's ratio of 0.35. Okay, so if you confirm that details are correct, then you close up the engineering data and get back to your project schematic diagram in Workbench. Okay, woohoo! Now the fun part begins. Okay, you open up your mechanical window by double click on the model tab here. Okay, so the first thing you need to do is you open up the geometry in the tree outline, and then you highlight the line body and scroll down in the details of the line body. Make sure that the materials are assigned to the body. So in this case, our material is the POM material, or the polyoxymethylene material. Okay, next up we are going to generate the mesh. Okay, in the mesh outline, you right click mesh and then you click the generate mesh. So let's say if I were to just accept the default setting in the mesh, so you'll see that the mesh defined here is very coarse, sangat kasar ni. So it does not appropriately translate to the geometry of the flexible gripper. So in that way, you have to modify the element size so that it will be much more finer, but not too fine, but just nice, so that it appropriately represent the geometry of the flexible gripper. Okay, as for our model, I think the element size of 9 millimeter is sufficient to represent the 3D model of the gripper. Okay, let's try this. 9 mm, click the mesh in the tree outline, right click and regenerate the mesh again. Okay, now that looks much more better. So if you want to look into the details of the mesh element and the total number of nodes, you can click on the statistics, and they will detail out the total number of elements and the nodes of the newly defined mesh. Okay guys, just in case your mesh does not show this 3D view as in my display, then you have to activate the tick shells and beams function. Okay, so you click on the display ribbon on the top side of your mechanical window, and then you enable the tick shells and beams feature. Okay, so from there you will get the 3D view of the mesh elements of this particular flexible gripper. Okay, now for the next step, you are going to define all the loading and boundary condition in our geometric model. Okay, so as shown in the figure on the lower right side of your screen, okay, we want to define the rigid points at this one end. So you have to include a fixed support condition at that particular point. So you can right click static structure and insert the fixed support, or you can go to environment and then you choose fixed support. So in the item by which you want to define the fixed support point, okay, please click the lower end of the flexible gripper as shown, okay, and then you click apply. So one vertex is selected to define the fixed point. Okay, now for the next step, we are going to simulate for the actuation direction, which resulted to the gripping effect as shown in the lower right side of your screen. Okay, in order to do that, we have to add on another loading condition. Okay, you can go to environment, okay, and you choose fixed rotation. So for the fixed rotation, you have to appoint it to this point, okay, as shown in the screen, and then click apply, one vertex selected. So in the fixed rotation feature or details, we have to make sure that rotation around x-axis is free, to say that it can rotate along the x-axis, but along the global y and z direction it is fixed. Okay, so you just follow this parameter in your system. Okay, however, that loading condition is not sufficient to illustrate for the actuation direction. Okay, so in order to visualize how the actuation looks like, we have to add on another loading condition at the same point, which is a displacement. Okay, so you can go back to the environment ribbon and then you choose displacement. So we are going to select the same vertex as we selected earlier. So you click that point and then click apply. And the next thing is we want to define how many displacement are needed for our simulation. So in this case, we want to illustrate, let's say, a 50 millimeter displacement downward. Okay. So in order to accomplish that, the displacement at the x direction would be 0 millimeter. The displacement in the y would be negative 50 millimeter to indicate a downward motion as shown. And let's just leave the displacement in the z direction to be free. Alright? Okay, now let us set up the analysis setting pula. Okay, so under the static structural tree, okay, you highlight analysis setting and then you look up for auto time stepping, make sure it is turned off, and you make sure the number of sub-step is 10, okay, to improve the simulation process basically. And then on the large deflection, you can turn it on, okay. Usually, we would turn on large deflection to include any kind of geometric nonlinearities. So therefore, it will give us a more accurate solution, but sometimes it would take more computing time lah, okay. Okay, finally, as the solution output, we are going to measure 3 items, okay. So the first one, we are going to insert the total deformation. So you right click at the solution label here, and then insert deformation, a total deformation. Next, the second output that we want to collect is the stress value. So in order to do that, right-click solution, insert. This time, you navigate to the beam tools and then you insert the beam file. So if you look at the tree outline, okay, under the beam tool, there are minimum combined stress and also maximum combined stress to represent the stress value of the flexible gripper. Finally, the third parameter that we want to measure is the gripping effectiveness. And in order to evaluate the gripping effectiveness, we are going to measure the displacement along a particular direction. Okay, so in that case, we are going to insert deformation, directional deformation. So which direction? So since we want to measure for the gripping direction, we are going to choose x-axis as the direction orientation. Alright? Okay, now since all the loading and boundary condition have been successfully defined, you can initiate the solver to run the simulation for you. Okay, so press the solve button and wait for the system to compute the results that you wanted. Okay, so now let us evaluate the results. Okay, so if you select directional deformation, you will find that the maximum deformation is located at the upper corner of the gripper, the red colored region, and the displacement is recorded to be about 52 millimeter displacement. Okay, so how do we measure the gripping effectiveness based on this data? Okay, remember the time when we apply the loading and boundary condition? Okay, we represent the actuation direction as displacement negative 50 millimeter downward along the y-axis. So based on that parameter, ANSYS calculated that the corresponding gripping direction is recorded to be 52 millimeter. Okay, based on these two data, we can actually measure the efficiency of the gripping using the geometric advantage value. Okay, the geometric advantage or the GA value is calculated by dividing the gripping displacement, which is the output measurement, divided with the actuation displacement. So based on our result, okay, the simulation showed that the gripping displacement is 52 millimeter, and the actuation displacement that we defined in the loading and boundary condition is 50 millimeter. So 52 divided with 50, we will get a ratio of 1.04. So in the context of measuring the effectiveness of gripping, so we can say that higher gripping will result to larger geometric advantage. Means that it would have more gripping displacement lah. So our aim for our next simulation is we wanted to optimize the parameter so that we can maximize the gripping effectiveness by increasing the value of geometric advantage. And in order for us to increase the GA value, we want to increase the displacement value along the X direction. Okay, so in the next video, we will be utilizing ANSYS Workbench to help us decide the best parameter to achieve the objective or the output that we wanted. Stay tuned!